Okay, so welcome to the Sunfleet webinar. Today's theme is looking at scaled systems, and we've got Anahita and Laverick and from Oshen, from Plymouth in the UK, and Alex Parker from Washington State in the US, presenting today. Quick housekeeping. Well, first of all, welcome to country and paying our respects for traditional owners of the lands on which we work and live. And a little bit of housekeeping for the Sunfleet network. So Sunfleet has recently put out a call for sponsorship for a governance meeting and for the next 12 months of operations. As many of you may know, we've all been endorsed by UNESCO, and this means that we have costs associated with running the USV network and getting data up to the GTS in real time. And so what we have is some sponsorship tiers. And we've got some pretty good marketing opportunities. As you know, we've got global reach to a network of scientists, but also to industry OEMs. And we're starting to get some inquiries with big industry. So if you're interested in being a part of our network officially, please reach out to us at this email address, admin@usvglobalnetwork.org. Please follow us on LinkedIn and help promote our work. And I would say if anybody has benefited from Sunfleet, then you should consider providing some kind of sponsorship to the network. We also have this OSM session coming up. This is a meeting in Glasgow in February, and we're doing this alongside the UXS Operations Centre at NOAA and the National Oceanography Centre as well. And this is really about scaled and standardized data for global impact for using uncrewed platforms. And this is generic uncrewed platforms, and we are welcoming ECOPs, early career researchers, industry collaborations, and cross-sector and cross-disciplinary research using uncrewed systems. So please consider sending us your abstract and joining us for the session in Glasgow in February. And I think that is it. And so without further ado, we'll welcome Anahita, and you can just share can you share your screen, or do I need to unshare first?
Yes, absolutely. Oh no, I need to send a request. Hang on. I've sent a request over. I think you need to stop sharing for me to be able to.
How's that? Masha's.
That's not going yet. Okay, can you see that? Cool. All right. Well, firstly, thank you very much for inviting me. In the next
Hang
15
on.
minutes, I'm going to provide a quick overview of our company and the platforms. Before I dive into the kind of robotic sea stars, just a quick introduction of myself. So I'm Anahita. I originally come from an aerospace engineering background, but I've now spent the majority in robots, and I co-founded and now run a company called Oshen based in the UK. So I've split,
Anahita,
yes.
sorry, I'm going to interrupt you. We can only see a little bit of your screen.
Oh, hang on.
I think we might need
Is
to
it
share.
like a quarter of the size?
Yeah.
Ah, um, let me try shift that. Does that now work? Is that now like most of the thing? I'm trying to keep you guys on it as well. Is that now visible?
Yeah, maybe show us the first slide. It's hard to tell if it's the complete.
I think it is
Yeah,
a complete one.
yeah. Okay.
Well, here's the thing. Can you read the text on that? If yes, then hopefully I've made it large enough. There's
Perfect.
not a lot
Yeah.
of text on there, so is that now kind of big enough for you guys?
Yeah, that's
Okay.
fine.
Cool. Well, yeah, basically all this says is that I'm going to go through kind of three different types of topics. Firstly is just talking about Oshen and what the platforms do, what sort of data types they collect. Then I'll go into some kind of past missions and different kind of places around the world we've deployed and what those kind of previous deployments have looked like. And then kind of some of the most exciting stuff is actually upcoming. Um, the title of this talk was actually about deploying wide area networks, and there's something really exciting to share on that I'd like to go into at the end. So, quick introduction to Oshen kind of at a glance. So, we make and deploy these really small autonomous platforms for wide area monitoring. The picture doesn't have a human in it, so just for scale, they're 1 meter in size, so really on the kind of smallest end. And the simplest way to think about them is as a controllable buoy, or buoy for the Americans on the call as well. And the core applications come from essentially deploying networks of these. So the kind of point behind kind of doing all the design to make them really small, easy to deploy, is that as a result, they're kind of easy to get out there and low cost, so you can deploy networks of these over a wide area. Now, kind of four key features to kind of take away and think about. So, in terms of the endurance, similar to other kind of long duration ASVs, we use wind for propulsion with solar and battery as our kind of source of power. That allows us indefinite operation in most latitudes. If you want to deploy in the Arctic, we have to think more carefully, but otherwise, we're pretty good in terms of long endurance. And when it comes to navigation, our speed is between 1 and 2.5 knots transit speed. That also allows us to station keep. And then in cases of light winds, we also have a backup thruster, which we use kind of maybe for a few days to station keep in a really precise area or to sprint to a certain location as required. In terms of scale, so as we said, they're like really small. We call it hand deployable. You don't need special equipment to actually get them out there. And in terms of the sensor payload, we primarily focus on metocean data, and we've also done some work on passive acoustics. Now, just a quick picture of it with humans in there for scale, that's a couple people just deploying it overboard. So typically you need 1 or 2 people to lift it from either a small rib or small research ship to get it overboard. And we've also done launches from beaches or pontoons, again, just by hand, and then autonomously sail it out. In terms of data types that we collect, so as I mentioned, we do some passive acoustics, but the primary focus that I'll be talking about here is essentially on the metocean data. So the standard sensor payload is wind speed and direction, air temperature, sea surface temperature, sea surface salinity, significant wave height, wave period, relative humidity, air pressure, and surface currents as well. Now, I think one of the most important things for a new platform, especially for people hearing about us for the first time, is the data quality and data evaluation. So I've got a couple different projects we've done on here that I want to talk about where we compared our data sources to trusted ones. So the most common thing that we do is, as a company based in Plymouth, UK, we have two moored buoys, one 4 miles offshore and one 20 miles offshore, both operated in conjunction with the Met Office. And what we do is we go outside there and we essentially station keep for about a week at a time for each new platform to check that the data quality is comparable. And on the right hand side there, you've just got example plots from a recent mission of air pressure and air temperature. Another one is that we've sent a Sea Star to the west coast of the USA, tested with Mbari under the Cinco program. That involved a moored buoy comparison as well, but we're co-authoring a paper with them, kind of focusing on a more full platform evaluation that once it comes out, I'd be very happy to share with people on this call. The Met Office Observations R&D team have also done a study comparing our Sea Star data to the outputs of their UKV forecast model. And then finally, the moored buoys off the coast of Plymouth, we've done very extensive data evaluation work with Plymouth Marine Laboratory, who are based locally in the same city as us. So I said I'd tell you a little bit more about the Met Office work. This is one of our kind of more exciting projects that I really like to highlight. Often when people see such a small platform, especially 1 meter one, their first instinct is to think, how can that survive some of the harshest ocean environments, isn't it just going to topple over? It's so small, it's only a meter. And although obviously many theoretical calculations can show it's fine, towards the end of last year, we said that we just put our money where our mouth is, send one into a storm and see what happened. So when the first set of winter storms came to the UK in October last year, we deployed a Sea Star from 2 miles offshore, sailed it autonomously 40 miles offshore. We then let it sit there station keeping as the storm passed overhead, and then we sailed it back home afterwards with no damage and picked it up at the end. So there's a lot of nice data from this, but the most interesting is the wave height. I'm just moving this so you guys can see it. So it's on the bottom right there. So if you can see the tiny boat right at the bottom of that graph, that's the 1 meter boat for scale. And the wave heights that we were recording as we went through it, the maximum wave height was 8 meters. This tiny boat was kind of going through. And then we compared it to the nearest moored buoy as well, just to check that the wave readings were reasonably sensible as well. And this is what really gave us robustness. If it can go through a storm with 8 meter wave height, it's probably going to be fine for most things we throw at it. So that was really nice in terms of demonstrating the kind of edge capabilities of the platform. We then also wanted to look at the data in more detail and make use of that unique data set. So in a project collaborating with the Met Office Observations R&D team, they ran a study on the Met Ocean data from this and compared it to their UKV outputs. And overall, there was really good agreement with the atmospheric parameters comparing especially well. And the results in the study were presented just a couple of weeks ago at the Royal Meteorological Society's Weather and Climate Conference, which was a really nice way to kind of get Oshen's data out there and discussed. So those are some of our projects that we've completed to date. Now a little bit about what's scheduled in the next coming years. So on this map here is essentially everywhere that we have deployed to date. So the small green triangles there is where Sea Stars have conducted successful operations before. And then the red triangles there are, we've got a busy 6 months ahead of us, places where we're going to be operating the next 6 months. So this is quite nice, being able to test in lots of different areas of the world. What's much more exciting is going beyond 2025, funded by ARIA, a UK research and inventions agency. We are deploying 50 of our Sea Stars into the North Atlantic, and the data coming from these Sea Stars will be used as part of a wider program to try and predict climate tipping points. So, at the start of this, I really wanted to talk about kind of the impact of really small, low-cost platforms and the fact that that unlocks this wide area network. This is our first project where we'll really be able to put this at scale. By putting 50 out there, we're really going to show what a wide area network can actually do for weather and climate prediction. And then just going to the kind of broader future outlook outside of this program, I really see a core kind of thing that's not been possible before with kind of traditional methods being these kind of targeted constellations of small low-cost platforms, potentially for different applications. Previously we've relied on this combination of moored buoys, drifting buoys, and then kind of potentially larger, more capable ASVs. Now I see kind of constellations of these small things always out there, kind of listening to different parameters. Two different applications or ways of using Sea Stars that I thought might be of interest that I wanted to finish on. So the first is on reactive data or kind of changing networks. So if we think about how we've traditionally designed observing networks, especially ones comprising of satellites or moored buoys, you can't kind of reactively change your coverage. You're not going to go and move a moored buoy just because your kind of area of interest has changed. Whereas a lot of the parameters we're measuring, I took temperature and salinity as one example, they're not uniform over an area. You might have a really sharp gradient in a certain place, and actually you would benefit from a cluster of observations at this sharp gradient, and then more sparse observations elsewhere. And if you have this kind of controllable network or constellation of Sea Stars, we're hoping that we can essentially cluster Sea Stars at the variables of interest, and then over time, again, just kind of change the density of this constellation as the variables of interest change in their kind of location and density. And the second application that I think is important is reactive data collection. So again, we've previously been had to kind of use quite long timescales when planning our ocean observing infrastructure. But if we are now able to have these kind of small things that are quite easy to just hand deploy, there are kind of transient events that we might be able to absolutely flood an area with observations for. So the most obvious example for me is, of course, extreme weather events, whether that's storms or hurricanes. So essentially, as something comes in, if you have easy to deploy platforms, you can flood an area with like 20 platforms, make sure you get good data for the week that you really, really need data, and then they can be recovered afterwards, no problem. But it goes beyond severe weather events as well. Let's say you've got kind of harmful algae blooms. Again, they don't last for that long. Like maybe you want to go collect loads of data there, or specific fronts that you want to measure. Reactive data collection could maybe start to change the way that we do research and much improve the way that we can understand these events. So that's really it from me. Just to kind of recap a couple of things. We've validated our measurements, we've put our sea stars out into storms, we're putting 50 out into the North Atlantic. We're very excited to get word out about what we're doing, and I'm very happy to answer kind of as many questions as you guys have for me. So thank you so much for listening.
Thank you, Anahita. We are going to hold questions until after Alex's presentation.
Yep, absolutely.
Alex, do you want to share your screen? And in the meantime, if you have a question for Anahita, please pop it in the chat and we'll come back to that after Alex has finished presenting.
All right, can you hear me all okay?
Yeah.
Great. Well, good to talk to you this morning, or afternoon or evening, wherever you may be. I'm Dr. Alex Parker. I'm co-founder and CEO of Astraeus Ocean Systems. We're based up here in sunny Bellingham, Washington. And following up, I feel like this was a really great pairing of seminar topics because Anahita really clearly laid out the kinds of capabilities that we could consider once we move to this architecture of disaggregated constellations of very large numbers of capable and reactive vessels. What I'd like to talk about in the technology we're developing at Astraeus is the sort of coordination systems that we'll need to make mixed fleet, federated fleet combinations of these kinds of vessels over very large scales cooperative and tightly coordinated for many stakeholders. So at this point in time, if we want to think about Sunfleet as it currently exists and how we imagine it existing into the future, it's comprised of a large and growing number of diverse and independently owned and operated uncrewed systems. So from a coordination standpoint, this is kind of a nightmare. How do we create a centralized system by which a user can make coherent plans around what data is being collected where, knowing what assets are available to them at any given time, and ensuring both good utilizations of the assets that we do deploy, but also not duplicative operations where any given asset could have been used for a particular set of operations and it was just unknown to the user at the time. So how do we coordinate these diverse systems across the global ocean? In one area we can look to, my background is also in aerospace and planetary exploration. I come from background developing technologies for NASA exploration systems and working in developing systems for lunar and asteroid exploration. And one space we can look, and the language of constellations, as we describe them in this case, is coming from the recent development in the last 20 years of constellations of low Earth orbit, Earth-observing satellite constellations from mostly private Earth-observing companies. So if you think about the ways that Earth-observing has changed in the last 20 years and the availability of reactive and responsive access to very low-cost satellite-based data, that's enabled in part by the transformation that's come about by low-cost hardware and the ability to launch very large numbers, hundreds and hundreds in some cases, of small low-cost satellites, but in another with sophisticated coordination systems such that any user who needs data doesn't need to understand the logistics of operating a constellation of satellites. So what does that system look like for autonomous vehicles at sea? So at a very abstract level, you can think about it almost like how you would abstract away the coordination of a server stack or a computer system. You have these different layers of coordination You have your user layer, which is us, the ocean stakeholders, the PIs, those that want to access the capabilities that we have deployed at sea. Underneath that, you might have specialized layers of for interfaces or doing inference on particular tasks, weather forecasting, fisheries management, what have you. From that would flow requests, task requests into something like a tasking engine or a scheduler that then flows those requests out to whatever available assets are at sea, collects data from those, and packages them up to send them back to the users. Now, this is super abstract, and we're going to get into more detail, and it'll make a lot more sense when I do. But one of the places that I want to draw a lot of inspiration from is talking about how another network that I've been involved with in the past, wearing my astronomer hat, is the development and deployment of a global observatory network operated by a private organization, the Las Cumbres Observatory Global Telescope. And their whole motto is, we want to keep you in the dark. The whole idea is to be reactive and responsive to transient events occurring in the universe, so that a user who might have data coming in from a space telescope or from their own observatories and wants to schedule follow-up does not necessarily need to know what observatories are currently operating, where they're operating. They just need to be able to specify their targets, data quality, conditions under which observations can be executed. That flows into a scheduler, and this automatic network of systems spread around the entire planet will automatically apportion those tasks out between the available assets to ensure that that user gets exactly the data that they want without having to know how to operate a global network of telescopes. So one of the nice things about LCOGT is that they published a ton of lessons learned about how to build scientifically responsive scheduler systems for globally distributed robotic observing systems, which sounds quite familiar. So while they've got the astronomy problem we solved from this presentation in 2014, we can think about this as, what's the ocean observing problem we're trying to solve? We want to accept requests from many users, all of the stakeholders in Sunfleet, at any time from anywhere with an internet connection, so that we could be responsive to local stakeholder needs. We need to be supportive of many different kinds of science. These platforms that are out in the ocean will be conducting science for climate studies, for meteorology, for ecosystem studies, for fisheries, for MCDR studies, any number of science topics. They need to be highly responsive to new input. Once you've got something, you need to be able to reprioritize based on what you understand your needs are right now, and not be locked into some strategy that was devised yesterday or a month ago. We also need to make sure that whatever assets we deploy, regardless of the unit cost, we're talking about building large, exquisite networks of capabilities. We need to ensure that we're utilizing the full potential of that ocean observing network, that we are packing it with observations all of the time, so no assets are going idle and wasting time. And finally, be this killer real-time observing engine. How do we use this to enable new and reactive and responsive types of data collection at sea? So this architectural overview of the way that they operate the scheduler for LCOGT is direct inspiration for the way that we at Astraeus have been developing what we call our maritime autonomy tasking engine. This is a platform that allows any user with an autonomous vessel, any owner operator, to essentially plug into an API that would allow that vehicle to be taken over by a coordination system that does these things. So that once your vehicle is integrated, any number of users that are accessing that tasking engine can treat it like part of a very large asset pool for executing their observations around the global ocean. So this is a more detailed schematic of the way that we're building the architecture of the maritime autonomy tasking engine. I may not go through this in great detail, but the key elements of it are this ability to provide intent inputs. What is it that you need executed? Describing the data sets, the locations, time, quality of calibration, any number of those kinds of characteristics in an abstracted way, so that you're not over specifying what you need. You don't need necessarily to execute this on a sail drone or a sea star. You need to specify the data quality, location, and our system will basically break that down into tasks through an analysis of those requirements in the task optimizer to determine which vessels are capable of executing your mission request. This then goes through and looks at ocean conditions, existing task load, identifies available vessels that can be tasked or retasked to execute available observations, and builds those mission profiles autonomously, submits them to the autonomous vessels, monitors the telemetry, and sends the data back as it's collected for data processing QA/QC. So This is sort of the same breakdown of that and a quick visualization of what one of our autonomous routing platforms does. So this is a list of all of the things that such a tasking engine has to be responsible for. It needs to be able to ingest mission requests from multiple users. It needs to be able to match tasks to vessels and select best platforms for availability, sensor fit, location, endurance, all of these things. It needs to be able to rapidly and consistently generate conflict-free routes for each and every kind of vessel under its control, from any location at any time to any other location and any other time at sea. This is really core to our IP stack, is this ability to extremely rapidly develop highly sophisticated route optimization for any time, any kind of autonomous vessel at sea, and then conduct this discrete optimization over all task requests and all available vehicles to identify the optimal strategy for deploying the existing fleet. So as a user, what that workflow would look like, or what it would look like for you as you logged in and submitted a task request, you could consider this I have identified a potential boundary and I would like one or more vehicles to execute a pass over that boundary and determine its precise location and profile. So you would submit that task request through an online portal. It could be any number of mission design front ends that are specialized for your specific application type. That task is then broken down by Mate into generalizable units that can be compared across different types of vessels. It then does this sort of matchmaking across available vehicles that can be at the location you need them to be at the at the required time, and carry the appropriate sensor suites, or return that this is an undeliverable task request at this time, absent deploying new assets. It generates this broad fleet plan where it has looked at thousands of possible combinations of fleet to task assignments. It conducts a global optimization of all potential deployment strategies and identifies the singular current strategy that is best and deploys those mission executable packages through something we call a vehicle response module to any vehicle at sea that is part of that task plan. Data is collected, it's delivered to the users, and we conduct post-mission audits to basically confirm that the vehicle performed as delivered, that the data quality was met, and we don't need to retask and repeat the mission. Determine billing requirements if the vehicles were owned by a commercial concern that is selling this data access, just like Planet or Earth observing platforms. So to test this, we've been building our own autonomy platforms. These are relatively simple coastal ASVs that we're going out and testing some of this software on. Largely, much of this development is being done in simulation. I'll show you some of those simulations in a second. We're actively building partnerships with OEMs to try to deploy Mate on their products, both as a value add to individual OEMs and manufacturers of ASVs. You can essentially go to your customers and say, it's trivial for us to conduct fleet operations when you deploy these in a particular location. You don't have to think about how to manage 10 different vessels. You're coordinating a fleet through this centralized C2 interface. And incorporating a new vehicle into the control of Mate is pretty straightforward. You build this, it's basically a big JSON file that we call our vehicle response module. It describes the performance characteristics of the vehicle and all the API requirements for tasking it. So we have a few mission design front ends that we've built for ourselves, and we've built a number of fleet simulators so that we conduct testing and scaling operations simulations. This is an example simulation deployment of 10 different vessels through Puget Sound, where they're being autonomously routed and rerouted through time to execute missions from the north of the Sound all the way to the south, and some border operations. This is just a quick look at what dropping a very simple mission requirement in. This is basically just a spot check, go to this location, take a picture. When you drop this into a live simulation, this is occurring in real time with 10 vehicles on deployment and currently tasked. That new flag that just showed up there is the new is the location of the new task that has been dropped into the optimizer. It is shown up in that task database, and there you just saw the optimizer identified a vehicle to retask to execute that, and it has shuffled fleet priorities so that every existing task is still also executed on time. So state of Mate, Mate is it's built as a microservice architecture, and we're basically building it piece by piece by piece. We have working elements for the fleet broker. This is the centralized source of truth that is the one unit that speaks to all vehicles and the unit that speaks to the optimizer and every other element of the system. Our task optimizer, our wayfinder, and all of these other elements. We're continuing to build out more and more sophisticated capabilities that will be required for full-scale deployment in the future. This includes long-term condition forecasting and advances in wayfinder approaches to handle very sophisticated boundary handling and condition adaptation. Adding simulator capabilities for other kinds of ASVs and even crewed vehicles in the mix, and a vehicle monitoring task sharing stack that allows a small number of users to coordinate and monitor a very large number of vehicles simultaneously. We're working toward some mixed vendor pilots, planning out pilot demonstrations, probably here in Puget Sound with vehicles from several different manufacturers so that we can demonstrate this optimal assignment of optimal capability across a variety of vehicle types. And if you want to help out but don't have a vehicle to talk to us about potentially incorporating in a pilot, we have a platform up we call the Astraeus Mission Planner, and it's there basically to collect mission asks. So if you have certain kinds of strategies or missions that you would like to see executed at sea, you can go and put a concept mission request into the mission planner. This drops into our large database of collected mission concept that we can use to stress test our simulations against. So it's very helpful for us if you have ideas about what you would like to see Sunfleet do in the future. If you could go and put some notional mission concepts together for us and send them in, and that will help us build Mate into something that will be useful for you in the future. So to close, I just want to have you imagine what Sunfleet could look like in a few years' time, where rather than it being something where there are sort of small groups who have access to vehicles that are communicating with each other through whatever channels they have, say email or text messages, and asking someone if maybe they could divert one of their vehicles or deploy one of their vehicles to get out somewhere, and adding this days to weeks to months sort of lag time on the ability to be responsive, and all of the complexity that comes along with managing the logistics of this large network of diverse vehicle types. And instead, something where you could log into a singular interface, design your dream mission, submit it, instantly know what it's going to cost, whether or not it's going to be executed, and be aware of it as it executes on this global planet-wide instrument that you can book with a single API call. I also want to prime your imagination for what this means for the ability for future software agents to interact with the capability that we're building. So rather than necessarily being a human on that back end, deciding what measurements need to be made, if you have a weather forecasting model or a climate model that can make a request, that can indicate where a measurement will be most useful for it, it can reach directly into this API and access the mesh of these vehicles without a human in the loop. This is a big part of the way modern astronomy is done. We operate these virtual event streams that come from our large surveys like the Vera Rubin Observatory that just came online and flow out to these follow-up facilities without humans having to wake up in the middle of the night and ensure that this is indeed something we want to be doing. So this structural ability has radically accelerated our way to study transient events in the universe, and Sunfleet's incorporation of both very reactive and responsive vehicles, these autonomous vehicles, that's one of their key capabilities, with something like the Maritime Autonomy Tasking Engine will give us a very similar window into transient and changing events in the ocean. So thank you very much.
Great stuff, Alex. Thank you. All right. Thanks both Alex and Anahita for your excellent presentations and for taking the time as well to share your knowledge and research with the community. So it's time now to open the floor to for discussion and conversations around these new concepts. So if you're willing, if it's not too late at night for you, turn on your video so we can see everyone's faces and have a discussion as if we're all sitting in the room together. That kind of helps people connect. And if anybody has any initial questions, is there anyone? Oh, good day, Fritz. There you are. It's nice to see all these good, familiar faces. Anyone want to start? Actually, please, if you can't find the hand tool, the raise hand tool, just unmute and start talking.
I'll just jump on and say, Anita, like great to finally at least see you virtually. We've been like circling around for like a few years, and it was really cool to hear about the like validation work with like Monterey and a couple of the different buoys. I think that stuff is something like definitely I've talked with Ruth and her team a lot about. It's like tricky and hard work and takes a lot of time to do. So I really enjoyed that part. I don't know, not much of a question, but
Yeah, no, likewise, like been seeing so much the stuff you guys do, especially with the ocean crossing, super cool. So it's nice to actually see you in person. And yeah, in terms of the data validation, like it was just like the earliest bit of feedback we got from people, probably just learning from like, previous previous attempts, like the feedback any sort of customer would give us 2 years ago is like you need to show your data validation. So that was like our big focus for quite a while.
Megan?
Yeah, yeah, this is just so exciting to see both presentations, and what a great pairing. And wonderful to see the validation of your USV, Anahita. And I'm just wondering, if you're putting out 50 drones there, how are you planning to coordinate that, and especially taking into consideration Alex's presentation?
Yeah, absolutely. I think that was a very good choice of two presentations because it complemented so nicely. I think stuff like what Alex is working on seems like it would be incredibly beneficial for the industry and the wider community if something like that became the standard. I actually hadn't even thought of that sort of thing and the benefits for everyone. Like, that's a really cool concept. Um, the Ocean specific stuff is basically a tiny bit different, and it's because um, the 50, like the way that we're planning the constellation is based around optimizing for like a certain type of coverage. Um, I'm trying to think what the simplest way to communicate it is. Essentially, we're funding a PhD to do kind of adaptive level constellation planning for sea stars that optimizes for the fact that, like, how do you use winds and currents to get to the right place? So it's not like one on one, I need data here, so I'm sending a sea star here. It's like, let's say take the extreme case of you're in the Gulf Stream, but you can only move at half a knot. There's actually research that shows you can still maintain a uniform grid of data if you have enough platforms out there, because as one platform is dragged away, another one goes and swaps in. And it's like this weird kind of optimization process to plan the constellation, such that, like, as some basically move away, let's say some of them break and need to sail home to like get a refit or something, other ones kind of go in. So we're focusing on kind of solving that short-term problem in a way that's like unique to the fact we're sail-powered platforms. But I like, it's nice to know about the stuff that like Alex is developing, because we know that, okay, that's a very niche thing to Ocean. We should probably make sure it's compatible with this stuff that's coming out, so that if a customer wants to like use Alex's tool, for example, to optimize like the deployments for them, all they need to do is kind of output the grid they need, and our kind of software that's very Ocean specific just organizes the sea stars.
Yeah, I'll just jump in real quick and say that we've been conducting these simulations, and this is one of the nice things about having these tools available, is that right now we're in a position where maybe we can't coordinate 1,000 real vehicles at sea safely, but what we can do is simulate coordinating 1,000 vehicles at sea safely and really start to understand the requirements for what it will take to reach certain kinds of science metrics. So in our case, some of the simulation work that we've done is exactly that. Let's say we deploy a mix of vehicles with particular capabilities. We have some of our own internal specs that we've been designing toward, and you wanted to ensure that there is no, based on every historical hurricane and typhoon record, going forward, you had a network of vessels deployed such that there were no past hurricane tracks that would not have had at least 3 vehicles that were available to do a crossing of that. What does that fleet look like? How many vehicles do you need? Where's their optimal positioning? Where do you optimally position ports on the surface of the planet so that you can be continuously supporting those fleets as they need to go back for refits? You can set things like maximum deployed lifetime. We did it for like 6 months. We have a completely solved solution for some standard vehicle types for the Pacific Basin. That's where we've run most of our modeling to date. and leveraging existing things like ocean currents and others for optimizing that strategy, so that you basically have a moving grid. That grid gives you constant spatial density or adaptive spatial density based on what the science is that you want to achieve. And so there's really cool things that we're right at the edge of being able to show what we could do. I think as we grow Sunfleet, and particularly as we go and look for funding support to demonstrate the kinds of capabilities that this sort of observing strategy will bring to the ocean, having these simulation tools so we can go and say, we've never had this capability before. What do you mean I could guarantee you that there would always be at least 3 ASVs in the track of every hurricane typhoon that forms from now on, with actually the number of vehicles you need to guarantee that is not that high. It's not that many with moderate performance assumptions. But yeah, it's a really cool time. And Anahita, we really ought to circle back, because I think your PhD, we've probably got some stuff we can share that might speed that process along.
Yeah, absolutely. And just to kind of like riff off that in terms of like why that the stuff Alex is describing is so exciting. Like we have certain specs, like minimum speeds that we need to make sure the sea stars can do in order to be useful to people, or at least to be like believable, like, oh, okay, it can go there. But let's say that with really smart simulations, we can show that platforms moving up. So let's say basically if the platforms move at half a knot, they're like 10 times cheaper. I doubt we could do that, but like let's say we could do that from an engineering perspective, and then we show that actually like if you deploy these under actuated robots with really smart simulations, you can guarantee that you'll always have some in the right place at the right time. There's a lot of applications unlocked by very intelligent simulations that like we've currently like not exploring that actually might be quite interesting to explore in time. So yeah, this is very fortuitous.
So this is Michael Jones in San Diego with Subsea Sail, and we've been watching your company, and it's great to see the progress you've made. We were developing vehicles that are sailing vehicles and then also can go underwater. And one of the problems is that there's no anemometer, for example, today that can work above water, go underwater, come back up, work, go underwater, stay down for a week or two, come back up. So we're developing, every one of our vehicles will be a METOC base, plus acoustics, and we'll start taking orders at the end of this year and start delivering in the second quarter of 2026. But there's a huge need for meteorological and oceanographic information, so it's inspiring what you're doing. My question would be, we use both Iridium and mesh network when we close together, and we've got a second vehicle we're developing, which is a multi-hull that will be a mothership that's got Starlink and things on it. But I'm curious, there's always that tension between capability, using the thruster, amount of batteries, amount of solar. I didn't see any solar on your wing sail, so it must be on the deck, at least, showing what you did. And given it's a meter long, we're about 1.65 meters. I'm just wondering how you balance that, the amount of solar and what kind of batteries. We're just moving to lithium phosphate, for example. We were nickel metal hydride before. So I'm just curious what you're doing from a battery point of view and a solar creation point of view.
Yeah, absolutely. So the sea stars we have right now, all of them have a solar panel on the deck, not on the sail. And then there's a really large battery in the keel at 100, well, large for our size at 100 amp hours that constrains a lot of the whole design as a result from a stability point of view. In terms of what we are planning to explore in the future, solar on the sail is definitely something we would like to explore. It makes sense. The reason why we've kind of not done it and we'll do it quite slowly is that it really changes your kind of stability calculations if you're having quite like when you start putting solar panels on the sail. And if you do try put solar panels on the sail and do it in a really lightweight way, it's then difficult to make robust like over really long periods of time. So we would like to do it, but I suspect like especially when you've got curvature in two ways as well on the sail, like hard to kind of meet this trade-off of like cost, stability, and also like getting the power benefit. In terms of batteries, like our battery choice was, I would say, like probably conservative. In next designs, like I actually think it makes sense to go smaller and lighter, unless you're going to super high latitudes once again. And battery chemistry, I think, is a really interesting one. You know, The ones with the highest energy density are less safe, so they're more difficult to ship around the world.
Yep.
What we do right now is actually kind of like an in-between, where we have one of the kind of safest chemistries that you can get for lithium-based batteries, but you still have to essentially build them on site, because they're difficult to ship as a battery as a whole. So it's a bit like both of them are quite interesting engineering trade-offs with at least like 3 different things you have to take into account.
Well, good luck with all your work.
Mike.
Yeah. Question for Alex. Are you considering doing anything like, are you considering the like mate system being open source? Just kind of the lead into that question is there's quite a lot of work going on in the defense world right now. Like the government has a big program that supports multi-vessel comms and heterogeneous swarms. Anduril's pouring in huge amounts of money to do this. L3Harris is pouring in huge amounts of money to do this. Havoc AI advertises that they do this. So there's all like in the defense world, there's an enormous amount of focus on doing this like heterogeneous control right now, and we've had to support a lot of it, and it all feels quite siloed and like they're all solving for the same wheels. And so like really like an open source system seems like it probably would move a lot faster than a lot of that and would be probably very relevant to like the scientific community.
Yeah, there's levels of what we're doing that we think there's just no way to do other than open sourcing it. And then there's other parts of it where we're essentially, you know, in order for us to operate as a company, we're looking at where the service provisions are that we can provide that everyone derives value from, that we can keep ourselves afloat as an operating company. And so there's certain parts of that stack, which is core IP, which will we put a bunch of effort in developing, which will probably stay on our end. But there's definitely a split of those two things. One of the key ways that we're thinking about it is essentially that there are enterprise grade variants of what we're talking about doing that we will basically be managing as a cloud service. But then at lower levels of sophistication and guarantee, we're talking to some open source partners right now about deploying this as a complete package that can be run rather than as a global service as a local fleet manager. So if you have half dozen vehicles that you can hand deploy somewhere, rather than being plugged into some global service, maybe because of comms limitations, maybe because you're operating in a closed body of water, you can basically load up an instance of Mate on edge hardware. Those simulations were running on edge hardware of 10 vehicles operating about 100 different missions. You can build and deploy your own fleet broker. So we're actively sort of determining where and how much sophistication we put into what is the free and open source version of this that's out in the world, and what of it we maintain as our core enterprise validated, verified, highly secure version that we're offering as a global service for groups like Sunfleet and other industry applications.
Thanks for sharing that. Yeah, it seems like there's like a couple of these different efforts going on, and like the group here like led that paper and like touched on some of this. But like in Florida, for example, there's like a surface and UUV, like the Gandalf tracker, if anyone's aware of that, which like a bunch of different heterogeneous systems push to, but it's like one heroic scientist who runs that system and is like quite old. And it's like, oh gosh, it'd be so much better if there's like a relatively more shared and moderated like central resource. And then it's like, okay, you get like tokens. It's like, Anita's platforms is like, it's like, oh yeah, these are approved. Here's like your token. And even like you could get tokens pretty early, but just say like, hey, the data quality hasn't been verified. But at least it's like,
Yep.
okay, we know this isn't like a random bad actor. It's like, so.
Yeah, that's exactly how it's structured. It's a publisher subscriber model. Once you have, we can generate an enormous number of tokens for individual hulls. Once that token exists and a discoverable VRM is found that you can that the system can understand and model the performance of the vehicle, it basically does a unit test to confirm that the vehicle executes missions as expected, and then it's ingested. It's part of the system, and it's just part of every asset that's being optimized over. Beyond that, though, we're also working to ensure that there's, even with this full service option that we're building, that there's a huge degree of permissioning, both to monitor what, they're based on local regulations in water, certain vehicles will only be allowed to execute certain missions in certain places for certain people. But when you deploy a vehicle, you might be doing this as part of an effort for a limited research fleet, and you don't want industry to touch it. An industry operator might deploy a vehicle into the fleet and only want a small fraction of the overhead time to be available for scientific researchers to use that mesh, because primarily they're using it for an industry application. Defense operators that are deploying thousands of defense vehicles around the world will have very specific restrictions in place to allow external operators to reach in to use meteorology data from those assets, but they can still do that. And so we're building that granularity into the system such that when it's optimizing over what vehicles are available, it's meeting all of those for your specific request. It's meeting all of those regulatory requirements, operational restriction requirements, and permissioning requirements on the hulls themselves, so that owner operators see their vehicles used only in ways that they're supposed to be used according to the owner operators requirements. And users are seeing the broadest possible array of available vehicles being turned toward the tasks that they submit.
I'm going to jump in with a question. Anahita, are your data going to the GTS? And how much? I'm noticing that you've got some pretty good collaborations with science. You're using PhDs and you're collaborating with Met Services, which are basically comprise PhD research scientists. And I'm wondering what have been the challenges for you with working within the scientific community, and science is your market, obviously. I'll leave it there. I've asked 2 questions now.
Okay. So what were the challenges working with the scientific community? I think for us, and what I should probably say is like science is not our only market. I think it's something that's very difficult to have as your sole source of revenue. Like the way that, and I guess like, my reflections on that is, you know, because a lot of the time people need to apply for grants in order to like buy or use your product, and therefore, you know, you can meet them. It'll then like, maybe 9 months later, they'll like know you and be excited and look for grants, and then 6 months later they'll apply for a grant, and then like the project would only start 18 months after that. So like as a result, that's very difficult for a company to have as their sole revenue stream unless you are super established. The reason that we do it, and I think other companies in our space are very similar, like Mike, I'm sure you're the same, like, a lot of like a lot of people, myself and people like me, like care about the ocean, care about our weather and climate, like if so no matter what, I want to make sure that we have a business model, and as a company, like we will always be compatible with science. We don't want to essentially shift our business model, for example, or the way that we operate in a way that closes out like one of the most impactful things the sea stars can do. But it's not going to be our only revenue source. Like offshore energy is also like a pretty hefty industry. And yeah, I wouldn't kind of suggest that for any startup founders. In terms of other kind of things, I think again, it's just I think maybe because we interacted with the scientific community like very early on in Oshen's founding, it wasn't like we came in with the tech bro kind of hat on and then had to adapt to science. It's like we started talking to scientists at the get-go. So we understood what they wanted. We understood that data quality was important. It's not like we came in kind of with a totally different attitude and had to adapt. I think again, like that's kind of hard. And starting at our premise kind of made things a lot easier. And listening to the needs like as early as possible kind of made everything easier further down the line.
And your data is
Oh,
going
sorry,
to
yeah, missed that. So, we're currently working to try get our data into GTS. It's like so I think what I can say about our current status is like it's not the data that's the issue. It's just like admin stuff, like getting the right Bufa format and like we're going through the motions, but it's like taking time to go through. Yeah.
Cool. Sunfleet can help with that. We're the official stream for taking data to the GTS globally. So, and we are very close to the end, and we're starting to lose people. we are looking, we require funding and support. So I'm going to put that call out again. If you have marketing budget and Sunfleet has helped your company or your organization, your individuals operate and market their product in any way, shape, or form, then you should consider having a conversation with us about how you can support us, whether it's with in-kind resources or sort of cash contributions for sponsorship, and in return you get like the marketing and networking opportunities. So now we're really losing people. Thank you so much, Anahita and Alex. Geez, half an hour went really quickly for that discussion. So we will see you all again at the next webinar. If there's anybody that's interested in presenting, please reach out to myself or Megan and let us know. So thank you, and we'll catch you all later.
Thanks,
Thank you.
everyone.
Thank you.